So form a sum of pairwise sorry, I mean you, because this is usually said in a technical way, so I'm just trying to form the maximum sum of product pairs once again. So this is maximizing this can also be set maximizing something called the dot product. It has a geometric meaning, but maximizing the sum of pairwise products, whatever corresponding. And the inequality that we will end up having from here, when we had taken the sum and maximizing the product, that was sort of AMGM, arithmetic geometric mean inequality, though we didn't say it in full generality. But we said it is in a slightly different way, sophisticated in the combinatorial sense. But this is a very, very powerful inequality, but yet it's very elementary. It's called the rearrangement, which we will end up learning from here. Okay, so I said too much. Now you guys tell me, what have you tried? What do you think how do you pair up the elements so that the product maximizes? So the sum, yeah. Yes, right? So that is the intuition, right? So Unam, do you see the intuition of why you should pair the biggest with the biggest? Yeah, it's kind of, now obviously we don't know, right? This will actually, but it seems like this is the right thing to do. And then 12 is the second. No, so this is wrong. 20 is the biggest, so you should pair it with the biggest. And then you have 13, so you pair it with 14. Then 12 you pair with 13, and so on, right? So the claim is, and this is, so it's an obvious thing, like if this is an MCQ, then you know that this is what you should do, okay? And you don't have to explain anything, okay? But you will not be 100% sure maybe, okay? So let's see. Claim is that 15 times claim is 20 times 15 plus 13 times 14 plus 12 times 13 and so on. The board? Some connection problem. Am I audible? Yeah. Okay. Is the yes. Yeah. Okay. Right. Okay. So meanwhile, Ishana, can you see the intuition? Why do you think this is the right thing to do? Yeah. Why? Biggest. What was the last thing you said? Biggest. Okay. Yeah, it's right. So, but you see, yeah, that's right. So that's the intuition. That is the intuition, right? It's kind of hard to explain, right? Exactly why it's true. Yeah, but it seems definitely true. Yeah. Okay. So I'm just waiting for now if he joins. Okay, he has not joined. Yeah, so maybe you can think of some nice ways to explain this, right? Maybe for three numbers, some using some uh, maybe total area formed by a figure or something. You can try to think. That can be an interesting way. So yeah, so maybe what I am saying is think of a geometric reason. Yeah. So I'm just saying is that if a1 is less than a2 is less than a3, and let's say b1 is less than b2 is less than b3, then if you make this rectangle, if you make this so with one side a1 and the height you see let's say I take the height to be b1 and you make this rectangle, and then you take a2. Now a2 you can just mark so that it's clearly smaller, and similarly b2 you can take smaller, right? So then you can take b2. So this is a2 and this is b2, the height, and then similarly you can take b3 to be clearly smaller. It's a3 and b3. Okay, and you want to say that this area is the maximum possible area, right? Using these sticks as kind of base, and these sticks b1, b2, b3 as heights, right? Is that is that the same? Yeah, you see that's the same question. Yeah. So because geometrically maybe you can explain, okay, if I take some other combination, then I can make that combination kind of fit inside this. Maybe you can do cut paste and you can make it fit inside. You can give an explanation, right? So think about that. Maybe that will can give you a very interesting proof. And such proofs are there for a lot of other inequalities, and it kind of makes you see. But I've never seen such a thing. So maybe you should think. Okay. So try it. So maybe like I'm saying, if you take a1 with b2 and a2 with b1 and a3 with b3, give an explanation as to why this will be smaller by showing that the figure you get here, again, you can plot it, can be made to fit inside this bigger one, maybe by some slicing or reflecting if needed. It will not directly fit, I can see maybe, but yeah. And it can be done, I think. It seems right. So try this as a homework. You'll get a very beautiful proof. But yeah, but we have to still give an algebraic proof because these things are not sticks, these are general numbers, so we have to write it. But such proofs are obviously legal because they are so, so correct. They are accepted. Yeah. So to show that this is the biggest, what do we do? So to actually show. So how to show without becoming technical? How to show? So let's try to compare this with another product. Okay, let's try to compare this with another product. If I take a product that differs from this first, by comparing with another sum of the products. If I compare this with something else, let's say I take this and with 13 I pair 15, and let's say I keep the rest of the things same. See, this is like just one step difference. Then can we compare this two and show which one is bigger? I mean, clearly we know which one is bigger, but can we show it? Sorry. Oh. First two. Right. So yeah, that's right. So then this is the same as this. And this, but how would you check this? One as a constant meaning? No, but see, every number with respect to 14 is not a good idea because the other numbers are really not. Yeah, I mean, you can do that, but you see, instead of 15, that could have been 150, right? Yeah, yeah. But I can understand. I mean, the idea is correct. I mean, if it works for 15, it should also work for 150. You can say, and that's right. But uh, yeah, but we want to do it in a in a way that we can, so that later on we can kind of generalize it, right? So I mean, what you're saying will certainly work, and you can just multiply out and check also. That's also correct. But what we want to show that we will only need the fact that 20 is bigger than 13 and 15 is bigger than 14. You see, I only want to use this fact that this is bigger than this and it is bigger than this. Okay, so you see, with that in mind, you can just do some factorization. Just compare things like this. Okay, yes, yes, yeah. So I'm just saying that you can prove this by this manipulation that I did. Okay? I just took the 20 common, right? And then I took the 13 common because that was the other thing to do, right? And then this becomes completely obvious that this is true. Is this okay? Oh, it's still breaking, right? So maybe there is some connection here. I don't know what to do. Uh, hmm. Is it clear now or is it still breaking? Still breaking. Is okay? Okay, then let's do. Otherwise, I'll change the connection. Certainly the Wi-Fi. Yeah. No, so all I'm just saying is, see, I've just done this manipulation, right? If you look at this first step, this is what we want to show. I just said, okay, let's not do multiplying out and so on, but let's just take the 20 common and take the 13 common. Okay, then we get this next step. And then I'm saying that this is completely obvious. Is it okay? Yeah. You see, no, but the point with this is that in this way, you can just show that if A1 is bigger than A2 and B1 is bigger than B2, then A1 B1 plus A2 B2 is bigger than A1 B2 plus A2 B1. Can you do this? Yeah, so just try this first. I mean, we know this is true, should be true. We have to just check it. B1 minus B2. Right. Good. And this is correct, right? Because this is correct, right? So you see, this is once again very simple. And you see, it only uses the fact that for two numbers, obviously, it just basically doesn't use anything, right? You can see. Yeah. So that's the thing. So even when we are doing, so the moral of the story is that even when we are, and this is about proving these things because we kind of know this is correct. But while proving, first of all, obviously we're proving it locally for two things. And if you remember, this was the similar approach we took when we were trying to maximize the product, right? We kind of said, okay, yeah, if two numbers are equal or close, then yeah, or if you make them less close, then they decrease and things like that, right? And this is also, we are doing this, and this technique can be now generalized to prove, but it's a little more technical to prove it. So we will not prove this inequality in full generality, but you sort of understand this is the way. Okay. But the main thing which is very useful for us is that even when we are taking numbers as examples, and this a lot of students, especially those who are very good at calculations, they kind of oversee this. When we see these inequalities for numbers with the goal of trying to understand it for general variables, then we should not use the full power of the numbers, right? If you see something curious, okay, 2020 is appearing 1313, so let me try to take things common and see. So you try to see the variable behind it, and you understand, right? What is a true criteria of things that, yeah, it's about 20 being bigger than 13. That's why I paired. So that's what I should use. And right, just like that, then the numbers and these variables will kind of guide you to proving. Okay. But if someone simply expands this and checks it's correct, but there's no insight in that. So that is the thing. Because basically that's the whole point. We're trying to prove things which apply for all numbers or large class of things. Okay. Right. So basically what I've shown is that if you so if you sort both the sequences in increasing order, pair the biggest with the biggest and the smallest with the smallest, and pairs the terms which are in the same rank on both the sides, and then add them up, then that's a maximum sum. So let me write that maybe. So this is the recipe which you know, but I'm just writing it. Multiplying elements of, and this is also kind of a greedy algorithm because at each stage you just try to maximize. Like when you start, you see 20 because you see the biggest first, let's say. When you just sort it, obviously, you see 20, then you see, okay, now I want to get the biggest using 20. So obviously I multiply with 15. And this is a greedy approach, right? You're just thinking in the short term and trying to make the max best. And it actually works. These kind of things don't always work, but this is a very simple situation, so it kind of works. Multiplying elements of same rank and adding up. Adding up gives a maximum. I mean, I shouldn't say adding up because this is already there in the question, but still, and gives the maximum. So now you can tackle questions of this kind, which can be disguised in other ways. Right. And really, this is what we have seen. Oh, sorry. What is happening? It is showing I can move it, but when I'm trying to move it, it is. Yeah. Okay. Now, why will this help us to prove? Because basically, we will show that if you have some other way, if you multiply the elements in some other way. Now, this is just the idea because the proof will get a little technical. Okay. The idea is that, yeah, if we multiply in some other way, any other way, right, then there will be some kind of cross, meaning that there will be some AI which is bigger than AJ, some INJ, right? And then there will be like BI, which will be bigger than some BJ. Now you can take some numbers, you can take say A5 and A15. You will, if you multiply in any other way, then basically you will end up uh, doing something like this. There will be this B5 and B15 such that you multiply the bigger one with the smaller one and the smaller one with the bigger one. Yeah. So do you agree with this? If you multiply in some other way, then you will end up doing this to at least some pair. Let me just say it in another way. See, what are we doing? We are multiplying the biggest with the biggest, and then the second biggest with the second biggest, third biggest with the third biggest, right? If you don't do this, then it means that there is some place where you have not multiplied the biggest with the biggest, right? So there is some place where you have not done the thing in order, right? And so you have done it in a wrong way. There has to be some place, right, where I've done it in a wrong way, which means something like this. And again, this is just an intuition. You can, it's not hard to prove, but you can think. But this is what you would have done in some place. Now you know that undoing this will increase the sum. Undoing this will increase. This is the undoing part. Okay, undoing this, right? I will, and this second, we can just prove it. This is simple. This is already be proved. Undoing this will increase the sum. And in this way, if you keep undoing all the bad pairs where you have kind of multiplied a bigger with a smaller and it's corresponding smaller with a bigger and so on. If you keep undoing this, you will arrive at this. And so that will be the biggest. This is just the idea. Okay. This is the way in which we proved the earlier thing also, that locally you start with an arbitrary thing and you show that from there you can move up and get to your claimed maximum. And this is why it's a combinatorial inequality, because there is no real algebra, or it's just this idea of combinatorial. There are more generalized versions of this and so on, but we will not do. For that, we have to understand permutations better. Basically, we are doing some kind of permutations. Okay, so this was the rearrangement inequality. So we'll stop here. I will just give you another problem which you should think about. Okay, or I have already given 2-3 questions. So let me see. Let's leave it. You just try these 3. Try the ones that I've given. Okay, and as I've said, because you should do the problem solving and so on, which I've said. So yeah,